Thank you for the opportunity of letting me present our work here. I am Chaim Shaul and I will talk about secure cache nearest neighbors classifier. The work was done together with Dan Feldman from University of Haifa and Daniela Rus from MIT. The motivation for our work is to develop a privacy-preserving k-nearest neighbors classifier. Privacy preserving means we have two parties, one call it the server with training data, and another call it the client with a query. And we have the requirement that the server does not learn the content of the classified object, and the client does not learn the training data except for the classification of its query. To see why this is important, you can think of a patient that wants to submit her medical data and get a diagnosis, but is afraid that the data will leak to an unwanted third party, such as the insurance company, or the hospital providing the diagnosis that prefers not to be able to read the sensitive data to make it easy for it to comply with privacy regulations. Looking ahead, we are going to introduce a variant of k-nearest neighbors, and our improved protocol will assume something on the data distribution. We are going to implement our k-nearest neighbors classifier with homomorphic encryption, so I wanted to introduce some notations of homomorphic encryption. So homomorphic encryption is a public key encryption scheme, which means we have a public key X with which we encrypt. We denote the encryption of X by X in brackets, and if we decrypt the ciphertext of X with the secret key, we get X back. In homomorphic encryption, we have two more functions, add and mul, such that add gets two ciphertext, X in brackets and Y in brackets, and the output, if decrypted, gives you back X plus Y. The mul function gets also two ciphertexts X and Y, such that the decryption of the output is X times Y. So we denote X in brackets plus Y in brackets as the addition of the ciphertext of X and the ciphertext of Y. If we write X in brackets plus Y, it means that we need to encrypt or encode Y first and then apply the addition, the add function. Similarly, we have X in brackets times Y in brackets. That is going to mean that we apply the mul function over X, the ciphertext of X and Y. So as you can see easily, that any polynomial can be computed over encrypted inputs. And theoretically, any algorithm can be expressed as a polynomial. In practice, people will tell you that homomorphic encryption is not practical. I want to give a quick summary of our work I'll be showing here. I'm going to talk about a variation of k and n, which we call k-ish nearest neighbors, k-ish and n. This variation is more HE friendly, meaning that it is more efficient to be implemented with homomorphic encryption schemes. We're going to show an even more efficient protocol if the distances to the query point are close to Gaussian distribution, meaning that the closer the distribution is to Gaussian, the better accuracy our classifier has. To do that, we introduce two new techniques. One technique efficiently approximates an average of ciphertext and even an average of functions of ciphertext. And the second tool is what we call double-blinded coin toss. With a double-blinded coin toss, we can make a coin toss in homomorphic encryption with probability P, where P is a ciphertext, and obviously the output of the coin toss is also encrypted. We compare our work to that of El-Mehdi et al., who showed a privacy-preserving protocol for computing KNN. The work of El-Mehdi et al. Needs two non-colluding servers, and they describe a protocol that securely computes the KNN classification with as many rounds as order of k log n, and as much communication as order of kn. Our solution, on the other hand, does not require two non-colluding servers, and requires only one round with constant size communication. We also compare our work to the naive HE implementation of KNN. The naive implementation requires a circuit of depth order of log n and requires order of n square HE operations. Our improved solution requires a circuit that is constant in depth and has only linear number of HE operations. So here's what we're going to talk about next. I want to remind you what KNN classifier is. Then I want to shortly describe the system we had built. Then I want to tell you the high-level ideas behind our cache nearest neighbors variant. Then we'll see some experimental results. First, let's recall what KNN classifier is. We are given a database of points, in this case in 2 dimensions. Each of the points is classified as red or gray. Then we are given a query point Q that we wish to classify. We do that by finding the K. In this case, K is 6. We do that by finding the 6 nearest neighbors to Q. In this case, we take the L1 norm, and we set the class of Q to be the majority class of its neighbors. As a motivational example, we built a system for classifying breast tumors. We used breast tumor data from the Wisconsin dataset. Here we see a projection of the data on the plane using LDA. The green circles are benign tumors and the red circles are malignant tumors. The data was originally 30-dimensional with floating numbers. We projected it onto various dimensions and scaled the numbers and rounded them to integers. In our system, the database was held by one party called server, for example a hospital, and the client, for example a clinic, wanted to classify a query tumor. And the thing is, the client does not want the server to learn anything on the tumor, and the server doesn't want the client to learn anything on the database except for the classification of its query. The idea in our system is that the client encrypts her query, sends the encrypted query to the server. The server homomorphically finds the k nearest neighbors, finds the majority class of them, and sends that class to the client. The client then decrypts and learns the class of Q. So now let's continue to describe the high-level ideas of our protocol. First, notice that k, as long as it's not too small or too large, does not change much the accuracy of the classifier. For example, look at this graph. The y-axis is the accuracy as measured by the F1 score, and the x-axis is the value of k. We see that indeed the accuracy decreases slowly from 97 to 93 as k increases from 20 to 300, and then it drops even faster as k increases further. On the other side, as k decreases, there is a sharp drop from 97% to 95%. So as long as k is not too small or not too high, our classifier should give similar results. Our second idea was that it is much easier to guess a threshold t such that there are approximately k points with distances smaller than t with high probability. Then for each point we can homomorphically compare t with the distance from the query and decide homomorphically whether to consider it as a neighbor or not. Now, guessing a good enough threshold t is more efficient than exactly computing the k nearest neighbors. And it is even more efficient if the distances from the query point to the database are close to Gaussian distribution. If that does not hold, then it just means we need to resort to a less efficient way to guessing the threshold t. For the cases where the distances are close to Gaussian, the algorithm we describe ahead is more efficient. Also, what this really means is that as the statistical distance to Gaussian distribution grows, the t that we guess will yield a number of neighbors that is farther away from k. And as we have seen, as long as it's not too much away from k, it still gives similar classification rates. Also, our analysis here is not tight. It is much more important that the left tail of the distribution be close to Gaussian. We are now working on another algorithm for k-ish and n that does not require anything on the distribution. And finally, empirically, the databases we checked on did in fact have distances that were close enough to Gaussian to yield good classification rates. That was for most query points. For example, here you can see two distance histograms for two random query points on the breast tumor database. These two histograms were close enough to Gaussian to yield a correct classification. Putting everything together, we get that such a threshold is easy to find if the distribution were Gaussian. All we need to know is the average mu and the standard deviation. Then the threshold t is given by this formula. So it remains to show how to compute the average of distances and the average of distances squared. Let's see next how to compute, or actually how to approximate, these averages. So let's see how we compute an average of the distances xi. To remind you, the xi's are ciphertext, which is why we denote them in brackets. To do this efficiently, we want to avoid division and avoid large intermediate numbers. We want that for reasons that come from the properties of homomorphic encryption. Since we established that we can be off by a little bit, I will show you how we approximated this sum. This approximation technique is the first tool I mentioned in the beginning. So we're going to see how to approximate the average of the ciphertext xi. The idea is to replace computing the average by computing a sum of Bernoulli variables. So instead of computing 1 over n times sigma xi, we compute a sum of Bernoulli variables sigma ai, where ai is 1 with probability xi over n. This is a sum of coin tosses, each one with a bias xi over n. Remember that in our case, the xi's are encrypted, so we need to toss a coin with some probability that we don't know. We will see how to do that in the next slide. We call this a double-blinded coin toss, which is the second tool I mentioned in the beginning. We call it double-blinded because the party performing the toss is blind to the probability and to the output of the coin toss. It is easy to see that the expected of the sum of the coin tosses is exactly the average of the xi's. Using this idea, we avoided the division by hiding it in the probability. And also, there are no intermediate values larger than the output, which is the average. So let's see how double-blinded coin toss can be implemented. Remember that we have a ciphertext xi and a plaintext, constant n, and we want to toss a coin with bias xi over n. So we don't know what xi is, and whatever our implementation is going to be, we cannot expect to know the output of the coin toss, because if we could read the output of the coin toss, we could repeatedly toss coins and figure out what xi is. Our solution was to draw a plaintext number r between 1 and n and compare it homomorphically to xi. That is, we apply a polynomial whose value is 1 if r is smaller than x and 0 otherwise. It is easy to see that the probability that r is smaller than xi is exactly as we wanted it. In our paper, we show that it can be extended and that it is much more powerful than that, as we will soon see. Remember that our goal was to compute the average, and we did it with coin tosses. As we said, the expected value of the sum of the coin tosses is exactly the average. Using Chernoff or Hofding, we can bound the probability that the sum is too far away from the average. Recall that to compute the deviation, we also need to compute the average of the squared distances xi squared. Again, we want to avoid the division, and we want to avoid large intermediate values. Again, we are going to use the double-blinded coin toss. Our coin toss idea can be extended to compute the average of squared distances xi squared. In fact, it can be extended to approximate the average of f of xi for a large class of function without explicitly applying f on xi. This is very useful because recall that xi are ciphertext and f might be a function that is inefficient to apply homomorphically. The details of that are in the paper. And so to recap, this is the protocol we propose. Recall that what appears in brackets means it is encrypted. First, compute the distances from the query to each of the points in the database. Then approximate the first two moments, the average and the average of the squares, using double-blinded coin tosses. Then compute the standard deviation from the first two moments, and then compute a threshold t based on the average and the standard deviation we have found. Finally, find the points that are nearest neighbors by comparing their distances to the threshold t and compute their majority class. Now, what is great about our algorithm is that the steps that involve going over the points in the database are embarrassingly parallelizable. Here we denote them with p. This means the degree of the polynomials we evaluate does not depend on n. This has implication in homomorphic encryption schemes, but we are not going to go into that. To wrap up and avoiding all the gory analysis, we showed that given n points in d dimensions and another query point q and a parameter k, our algorithm finds the kappa nearest neighbors where the probability that kappa is far from k is bounded by something that is exponentially small. Now let's see some of the experimental results we have shown. The results we will see now were obtained by running our system on the breast tumor database I mentioned earlier. Just as a reminder, the database is part of the Wisconsin dataset. It contains 569 tumors, 357 are benign, and 212 are malignant. We projected the data onto subspaces of dimensions 2, 3, and 5. And we scaled the data to a grid of integers with various sizes of grids. We ran our system with the HElib library version 1, which is the older version. We ran it on a server with 16 cores of Intel Xeon with 2.2 GHz. We show how the size of the integer grid we scaled and rounded to affects the running time and the accuracy of our algorithm. You can see on the right graph, the grid size is given as the x-axis and the running time as the y-axis. And we see the running time in blue, yellow, and red lines. The blue line is the running time for the database projected onto the two-dimensional subspace. The yellow line is for the projection onto a three-dimensional subspace. The red line is for the projection onto the five-dimensional subspace. We can see that increasing the grid size increases the running time. On the left graph, we see how the accuracy changes with the grid size. The accuracy is measured with F1 score, which is the y-axis. The dashed line at the top is the accuracy of the exact k nearest neighbors on 30-dimensional space on floating point. This served as a benchmark for us. We see that our k-ish nearest neighbors classifier performs worse than the exact KNN. That is expected since our algorithm has a probability to guess a bad choice of threshold t. And this probability depends on how Gaussian-like the distance distribution to the query is. We see that for a large grid size, the accuracy of our k-ish nearest neighbors algorithm converges to be a little less than the benchmark of the KNN. That is 97% for the KNN and 91% for the k-ish nearest neighbors. We also compared our algorithm to the solution of El-Mehdi et al. And to the naive HE implementation. This comparison was made on the dataset described in the paper by El-Mehdi et al., which is different than the tumor dataset. Again, as expected, the accuracy of our classifier was a little worse than the exact k nearest neighbors classifier. That is expected. Compared to El-Mehdi et al., our algorithm has significantly lower communication cost, and compared to the naive HE implementation, our algorithm has significantly lower CPU cost. And I do measure it by CPU cost and not by time because these algorithms are embarrassingly parallelizable, and it is easy to adjust the running time by adding or buying more CPU. In that sense, our work and this comparison is really interesting because it allows for the user to trade off communication resources for CPU resources. And depending on the prices of CPU and communication, one can develop a hybrid solution that runs partly with El-Mehdi et al. Solution and partly with our solution. Of course, as HE schemes become faster, then our solution will be more competitive. Specifically, the running times were obtained with the older version of HElib. So to conclude, we said that the choice of k can be loosened and can be replaced with some kappa close to k. We call this k-ish nearest neighbors. To make it easier, we guess a threshold t such that with high probability there are approximately k neighbors whose distance is less than t. There are many ways to guess such a threshold t. If the distances are close to Gaussian distribution, then we showed how to better guess the threshold t using the average of the distances and the average of the squared distances. We introduced a new tool to approximate averages of functions of ciphertext and used it to compute the average and the average of squares. This approximation uses another tool we introduced, which we call double-blinded coin toss. In the future, we are going to improve our algorithm and improve its running time and accuracy. We are working on extending our algorithm so it would not assume anything on the distribution of distances. We also work to approximate more machine learning algorithms and also looking for more applications for the new tools we introduced here.